All right. Hello again. Thank you for joining this session where we are going to discuss about efficient multi-physics approach to design of an electric drive. And to present this topic, along with PowerSys, our senior support engineer, Dheeraj Boba, we do have our partners, Hexagon MSc. We have Alexis Talbot, Travis Heisted, and Anup Paul, who is going to cover this entire topic. And to introduce the first speaker who will take over is Dheeraj Boba. Dheeraj Boba is currently working as a senior electromagnetic design engineer at PowerSys Solutions. He has held position as applications and project engineer focusing on low frequency electromagnetics in the past. He has obtained his PhD and master's and bachelor's all in the field of electrical engineering. His current research interests include high power density electric machine design, control, and optimization techniques, focusing on traction and aerospace applications. With this, I would invite Dheeraj onto the screen to start the topic. Thank you.
Thank you, Wade, and welcome everyone again. So this session is, as Wade mentioned, we'll be partnering with our technical partners, Hexagon MSc, and the first part of it will be a precursor to show how the force and loss calculations are performed in JMAG, and then what is the process to import that into MSc tools, and that's where our colleagues will take over. To just give a quick introduction to JMAG before we jump into the main part. It's in general, we can use a lot of different type of applications that can be simulated in JMAG. It's typically most of the examples you've seen towards the past couple of days are motors or generators, but in addition, we can also do transformers, actuators, induction heating, sensors, bus bars, circuit breakers, reactors, etc. The fields in which these applications are, at least for our customers that we usually see, are in automotive, aerospace, home appliance, digital equipment, and factory automation, and also, of course, in academic research. The magnetic field analysis module, that's the primary focus for us now in this session, at least from my side, and that consists of both 2D and 3D magnetic field simulations. And the basic flow chart for the implementation is shown here. Really, we bring in a CAD model, apply the material properties, we apply the study properties, which is basically the boundary conditions and any kind of coupling, circuit coupling that needs to be associated with that. And then we apply the magnetic load conditions, generate the mesh, run the analysis, and post-process the data. So the type of analysis that can be run are either electrostatic, which is not time-dependent magnetic fields, or the frequency or harmonic analysis, where everything is calculated in the frequency domain, and the transient analysis, which is the most common part, where we are looking at time-dependent varying components. So with that, just a quick overview. This will be introducing JMAG capabilities in terms of EM force calculation and the motor loss calculation. Let me jump into the first part of it, which will be the force calculation. To briefly look at the magneto-mechanical system or the phenomena in electric machines. First, we'll have an electric power supply that is fed into the electromagnetic system, or in this case, it'll be the electromagnetic solver, which will give output as the forces, or for instance, torque or electromagnetic force. And that will be fed into the mechanical system, which will calculate the displacements generated by those forces, which can be fed into an acoustic environment or acoustic simulation environment, where we can estimate the noise generated by those forces. The typical flowchart for that is here. Basically, we'll give a resultant current or a direct current input, which should include the fundamental components, any non-sinusoidal components, harmonics, unbalanced or eddy currents associated with the electromagnetic fields. And also the permeance coefficients from the analysis will also be derived for the slot, any eccentricity in the rotor, etc. And this is all accounted for in the electromagnetic computation, and the flux densities are generated. Using that, the EM forces are calculated, and that's where the data is sent out to the vibration estimate or acoustic simulation part. And in this process, we can also add friction or any external mechanical forces that needs to be considered into the system. Coming to the electromagnetic force calculation, JMAG has multiple options. We're looking at the menu that's available in JMAG. Typically, there's three: Nodal Force, Lorentz Force, and surface force. The same is applicable for torque as well, but basically torque is radius times force, so it's the same as that one. To go into a little bit more detail, excuse me, the nodal force is something that is used to calculate the force on magnetic material parts in the electric machine, and it's basically calculated on each node. We'll go into further more details on this in a little bit, but basically, if you're looking at a motor, ideally all the magnetic materials, which is the steel, magnets, etc., that's where nodal force is typically used. And looking at a vector plot for the magnetic force, this is how it looks like on the surface of the stator. And then we have Lorentz force, which is something that can be used to calculate force on conducting material or essentially non-magnetic material, such as coil. In this case, we're looking at a transformer and some example of how it looks in the output, looking at a vector plot of the distribution of Lorentz force. And the last one is a surface force calculation. This is where magnetic material is in contact with each other. And in that scenario, there's shared nodes between the materials, and that's where nodal force cannot be applied. And we have to switch to a surface force calculation. And again, here's an example of an actuator with the plunger moving. And at the end of the transient, the plunger is in contact with the metal part on the top, and this is where a nodal force is not applicable, and we have to switch to a surface force calculation. The method for nodal force calculation, a little more, some more detail here, is basically, as I said, has to be applied on magnetic material, and the net force is calculated by estimating the Maxwell stress tensor, using a Maxwell stress tensor method, estimating the force on each node. And the net force is a summation of each force vector on the element. So that's how the nodal force is calculated. And this process will be repeated for every mesh element in the part that is this force condition is applied to. Then we have the surface force calculation. As I said, this is where when the magnetic material are in contact with each other. And in that case, a integral air region is generated around the surface, and a dense mesh is required to estimate the surface force for all the elements on a given surface. There are some downsides to it. Is that, of course, as I said, the dense mesh is required, which kind of increases your calculation time. But then the error in this method is minimal because the variation of flux densities or flux in that air region due to its low permeability is quite minimal. So the noise or variation in this method is lower. And then we have the Lorentz force calculation method. As I said, this is only for conducting or non-magnetic material. And in this case, Lorentz force is calculated based on the current density distribution in the mesh element and also magnetic flux density at the center of the element. It's a cross product of that. And once again, the total Lorentz force is the summation of individual forces on all the elements. So that'll be the brief introduction to the force calculation method in JMAG, or methods available in JMAG, and we'll switch over to the motor loss calculation. And here, there are different loss components, of course, but I'll be focusing more on the iron loss, and again, very briefly. So to go over a rough outline of the Magneto-Thermal phenomenon of the machine. Once again, the input will be the power supply or the input currents voltages to the electromagnetic system. Now we are calculating the Joule losses or eddy current losses or the iron losses coming from the system, and apply that to a heat transfer system or analysis environment here, calculate the heat flux, and that will go to the thermal environment and estimate the temperature of the machine. To do that, we need to understand not just where the heat is being generated, but also how the heat is being transferred inside the machine. So for example, we have here a complete motor with its stator core, rotor, and the external housing. We can use the electromagnetic analysis to estimate the copper and iron loss in the stator, and then apply to a thermal analysis, which shows the heat flow direction and the temperatures over time. Like I said, there's different types of losses that we should be considering. Mechanical losses are not a part of the electromagnetic system, but these need to be added externally for the total thermal analysis. But we have iron loss, copper loss, and any stray losses. In this case, iron loss is a summation of the hysteresis loss and eddy current losses inside the lamination. And of course, eddy current loss also includes both classical and excess losses as well. So as I said, I'll be focusing on the iron loss calculation process quickly in a couple of slides here. Basically, the process for that is we'll perform the magnetic field calculation, and each mesh produces its flux density distribution over time. This information is used to generate an FFT, and the amplitude and frequency of those B fields are calculated. And then we'll have the measured iron loss data either from the manufacturer or by performing like an Epstein test. We can also get the complete loop, hysteresis loop information. And this FFT is used to estimate the total path taken by the material in the mesh element. And the iron loss can be estimated using that information. Yeah, so as I said, the loss properties are two different types. It's either the loss curves, which give the loss per unit volume, or the B and H curves that show the complete hysteresis loop. Either type of input works with JMAG, and these are usually something you can get from the manufacturer or your supplier. And JMAG has an extensive built-in database that are coming from the suppliers or the manufacturers, which include the iron loss tables and the iron loss data for each material. So all of these can be used in the iron loss calculation. So in the end, we're looking for the general process in exporting the information that's generated both from force calculation and iron loss estimation in JMAG electromagnetic analysis onto MSC tools. So for this process, we'll be using what we call the multi-purpose file export tool. This is a part of JMAG Designer, and when you install Designer, this is already available there. And once you generate or once you finish your electromagnetic analysis, you can simply bring in your external CAE tool or the mesh from the external tool and link it to the multi-purpose file export tool and combine the nodal information or the mesh information from JMAG onto the CAD model for either thermal or acoustic analysis. Now, with that, I will introduce the next speakers.